Sometimes a road grows two thin black lines overnight, stretched from one shoulder to the other. They look like temporary cables, yet every passing tire produces a tiny event inside them. By morning, that quiet strip of rubber has measured how the road was actually used. The obvious guess is construction. Perhaps power, communications, or a repair crew forgot something. But these lines are usually sensors, not utility cables, and they are meant to be driven over. Their job is temporary observation. Count movement now, then disappear before becoming part of the pavement. The mechanism starts when a tire flattens the hollow rubber tube against the road surface. That squeeze launches a short burst of air along the sealed tube toward a box beside the lane. Inside the box, an air switch converts the pressure change into an electrical pulse, one axle event. With one tube, the counter sees a timeline of impacts rather than a neat list of cars. A two-axle car normally produces two closely spaced events. A longer truck produces a more complicated pattern. Software groups those pulses, but the raw physical measurement is still each axle crossing the tube. Add a second tube at a measured distance, and the same front axle strikes tube A, then tube B. The counter knows the separation and records the time gap between those two impacts. Distance divided by time becomes speed, often from a spacing of roughly 1 meter in a standard survey. The sequence also carries direction. A then B means travel one way, while B then A means the opposite. That only works when the layout isolates the lane and the counter can match corresponding axle events. The tubes are therefore less like a tripwire and more like a tiny timing gate spread across asphalt. Now the pulse spacing inside one vehicle becomes another measurement because axles are arranged differently. A passenger car, a bus, and a multi-axle truck leave different timing signatures as they cross. Classification rules translate those signatures into useful groups without photographing the driver or reading a plate. There is an important trap. Two axle pulses do not necessarily mean two vehicles. A simple tube count may need an axle correction factor before it can represent vehicle volume. The mix matters because a road full of trucks contains more axles per vehicle than a road full of cars. Most tubes are temporary because the survey question is often temporary. What happens at this location this week? Federal guidance describes short counts lasting a day, 2 days, or 3. Some councils commonly collect a full week. Move the same portable kit to many sites and a small team can sample an entire road network. That portability is the design advantage. Rubber tube, roadside counter, battery, fasteners, and no deep excavation. The equipment is relatively inexpensive, uses little power, and can be retrieved for the next survey. Its simplicity is not crude engineering. It is a deliberate match for short-term, geographically distributed measurement. A few days of traffic cannot describe an entire year without context, because weekdays, seasons, and locations differ. Agencies compare short counts with patterns from continuous stations and apply day, month, or axle factors. That process turns a temporary pulse record into an estimate such as annual average daily traffic. Permanent detectors solve a different problem by watching selected sites continuously through embedded loops or other sensors. Portable tubes provide geographic reach. Permanent stations provide the long calendar needed for adjustment. A monitoring program becomes stronger when those two kinds of evidence are combined rather than confused. The idea is nearly a century old. Simple pneumatic road detectors appeared in the 1920s. Cameras, radar, magnetic sensors, loops, and modern analytics arrived, yet the rubber tube never vanished. For a short survey on the right road, the old pressure pulse can still be the most practical measurement. The right road matters because tubes have limits. Dense stop-and-go traffic can blur which pulses belong together. Snow, very low speeds, multiple lanes, heavy flows, or poor placement can reduce accuracy. The same exposed rubber that makes installation easy also leaves the sensor vulnerable to tire wear and damage. Even a clean tire strike can create rebound pressure, like a small echo traveling inside the tube. Counters therefore use a minimum pulse threshold and briefly reject new inputs after a valid event. Calibration and field checks separate real axles from echoes, faults, loose tubes, and impossible speed patterns. There is also a human limit. Installing and securing tubes means working at the edge of moving traffic. High-volume roads, complex lanes, poor pavement, or unsafe access may require a different sensor technology. Temporary does not mean casual. Safe placement is part of the measurement design. What comes back is more than a car count. Agencies can study volume, speed distributions, and vehicle classes. Those observations support road planning, safety analysis, engineering studies, and the timing of future investments. The tubes make a road legible by converting ordinary wheel impacts into a structured dataset. They do not weigh the vehicle, recognize the driver, or explain why the trip happened. They record pressure pulses and timing. Every larger conclusion depends on layout, classification rules, and quality checks. The honest result is a measured sample with known limits, not an all-seeing cable under the tires. So why are black tubes stretched across the road? Because tires can power a remarkably useful measurement themselves. Tube pressure marks each axle. A second tube reveals time and direction. Pulse patterns suggest vehicle class. Subscribe for the hidden reasons behind ordinary things, including the sensors buried permanently beneath busy intersections.